Alrighty, gang, we're going to show that the melting of water is spontaneous, which means it takes no additional energy to melt it at 10 degrees Celsius and 1 bar. And we're given the enthalpy change of melting, of fusion, which is 6.01 kilojoules per mole, which means it takes this much energy to melt a mole of water. Now, there's many ways to do this. I have other ways, and you can find them in the description below, but in this video, we're going to use the fundamental equation of chemical thermodynamics, which is delta G equals delta H minus T delta S. And in this kind of integrated form, we're assuming that temperature is constant. Now, another assumption we're going to make is that the enthalpy, H, change, the change in enthalpy, and change in entropy, S, is constant. So this means that regardless of the temperature at which we melt the water, delta H is the same and delta S is the same. So this number doesn't change regardless of the temperature in which we melt it. Now it does change, but we're assuming it doesn't. If we do, and now bear with me, we got some notation here, but it's not too bad. This is just specific to the question. This is the change in fusion. So in our case, it's the change in melting at 10 degrees Celsius, and it's under standard state, so a constant pressure of 1 bar and in its pure form. And we're saying that this is equal to the enthalpy change at 0 degrees Celsius because delta H doesn't change depending on the temperature. Doesn't change based on the temperature. Minus, this is the temperature at which we're melting it, which is 10 degrees Celsius in Kelvin, and then the change in entropy. Now, to get this change in entropy, we're going to look at the temperature in which the liquid and solid phases are in equilibrium, which is at 0 degrees Celsius. And if they're in equilibrium, then the change in Gibbs energy is 0. And we can plug this into our equation, fundamental equation, right here. And now we can solve for the entropy change, which gives us an expression in terms of the enthalpy change, which is good because we're only given the enthalpy change in the question here. So we can plug this into our equation here. And at this point, we're basically done. We can plug in our values, our 6.01 kilojoules per mole, plug that into our calculator, which gives us a change in Gibbs energy of negative 0.220 kilojoules per mole. It's negative, which means the process is spontaneous. And if it's spontaneous, then the total entropy change of the universe is greater than 0. We can solve for the entropy change of the universe as negative delta G over T. Let me know if you want me to derive this equation, but if we plug in the values, then we're left with a positive number, so the total entropy increases, which is good. Okay, y'all, hope that was clear. You can check out my other ways to solve this type of problem, but best of luck on your finals, midterms, and all that stuff. It's not an easy course, but you can do it if you continue doing many, many, many problems. I'll see you in the next video. Cheers.